In section 3.1, we're going to talk more about the derivative of a function. So we distinguish between the derivative of a function, so that actual function, and then the derivative of the function, the derivative evaluated at a point, which will be a number. So the derivative function, we say f prime of x or dy dx is known as Leibniz notation. Is given by the limit as h goes to 0 of f of x plus h minus f of x all over h. There's other notation we see, y prime, df dx. Here we see the derivative as an operation applied to a function f of x. So it shows that operation of taking a derivative is applied to whatever's inside that bracket. In the yellow, we see we have a couple of different ways of finding the derivative evaluated at a point, kind of just a twist on the formula we use for finding the derivative function is instead of using the x, we can plug in the a as we see in that second version, and a little different twist on that with f of x minus f of a over x minus a, the limit as x approaches a. Both of those will end up giving you a number, which is the derivative evaluated at a. In the next one, we see that in the green here, we have the graph of y equals f prime of x is given, this is y equals f of x in the yellow. And we're going to try to come up with the graph of y equals f prime of x. And in particular, can we see what happens at the corners, cuffs, and vertical tangents? So to start, we can see, we're going to get some horizontal tangents in here. We know that that's going to result in x-intercepts. That's a good place to start. We can see that as we join the graph here, the derivative, the slope of the tangent lines are positive. So we're going to start with some positive number as we work our way down towards this x-intercept. We can see that this graph here looks like maybe a little piece of a parabola, in which case we would expect to get as a derivative 1 degree less, we'd be looking for a straight line. So again, it's going to go positive down to negative in here. And then it looks like a pretty nice transition there. And so we continue to go down, and then it's going to be a 0 here as well. So we're in the negative, and then it's going to work our way back. So we're going to bend and come back up in here. And then that's going to continue going positive up until we get to this looks like a corner point. And so that's going to be a place where the derivative is going to be undefined. Now we switch to this in here, looks like a straight line. And so that's going to give us just a derivative that is equal to the slope. So I'm going to estimate that that looks like it's positive, and we're going to go somewhere to in there maybe. And now we switch to a horizontal line in here whose derivative is going to be 0. So we'll get a horizontal line segment on the x-axis. And that looks like another corner point there. And then we're going to get into some negatives going down to, this is supposed to be a cusp, which means those tangent lines are going to fall off the cliff and go to negative infinity. So it's going to drop down and do something like that. On the other side, we see the slopes are very steep positives. So it's going to be coming from positive infinity, and then it's going to gradually become a smaller positive in here, but doesn't look like it's quite ever going to beat 0. And then it's going to take off again up to positive infinity. So something like that. And then we have, whoops, hold on there. I'm jumping the gun a little bit. Because we said that our, okay, so I'm going to stick with that. So we have this thing is going to take off and go up. And then on the other side here, we have very steep negatives. So it's going to come from negative infinity down in this direction. And as we work our way down, it's going to get really close to 0 and then go back to negative again. So I'm not sure if we actually hit 0 or not. But then as we work our way down this way, this is supposed to be a horizontal tangent, or vertical tangent rather. And so we're going to fall off the cliff and go to negative infinity. So we're going to get another vertical asymptote there. And then on the other side, we're still very steep negatives. So unlike the cusp where we got the asymptote and they went to different infinities on the vertical tangent, we're going to go to the same infinity on either side of the vertical tangent. And then these are going to, looks like it's approaching an asymptote as we go off to the right, but it's always going to be slightly negative, and so we're going to approach 0 as an asymptote coming from below. Okay, moving to the next one, now we have to change gears and try to go the other direction. So here we have the graph of y equals f of x. So the blue here is y equals f of x, and we are going to try to find here what is y equals f prime of x. And we're told that this original function, no, I'm sorry, we're graphing f. This is f prime. Let me get to the right color there. So we're given f prime of x, and we're going to try to find f of x. So we'll make the f of x be in the yellow, and we're going to try to make f of x continuous. So here we see if the derivative is always this constant, that must be a straight line, is going to be the original function. And since this is a positive number, we must get a straight line that's going to be rising from left to right. Now, we don't have any y values, so you can scale this anywhere you like. You could initiate this anywhere you like. I'm just going to choose to make it go something like this. Now, it's undefined at this place where we have the two open circles, but since our original function is continuous, then I'm going to make that be a corner point. So this is actually showing us a corner point by seeing these two derivatives that are horizontal lines. So this is now going to be a straight line that has negative slope, so we're going to come down something like this. And this could be anywhere up or down from here. So there's no known y values there. So now we have another place where it's undefined, so I'm going to make that be another corner point. Now what we have is a straight line that has a positive slope, so then that means that must come from a parabola that is opening up. So I'm going to do something like this. And then we're going to transition into a parabola that opens down because of that negative slope, and we're going to be continuous, so I'm going to do that as we're heading down to here where we're going to get a derivative of 0, so I'm going to do something like that. So it looks like it's ready to be maybe a relative maximum, but then it's going to go back to increasing again because our derivative is positive. So this is going to take a turn and start to go up here. Now we see that this is going to the same infinity on both sides. So that means as I come in here, then this must be a vertical tangent. And you can see the derivative is positive, and then it's positive again. And then it's going to go and approach 0 by the time I get to here. But then it's going to turn and go positive again, but this time we're going to go to different infinities. So that's going to make this be then a cusp, so that the slopes of the tangent line go from very large positives to very large negatives. And then it's going to be, our derivative is negative, so it's going to decrease, but then approach 0, so there's going to be approaching a horizontal asymptote as we head off that way. Tough stuff. Let's move to a new panel here. Pause it a moment and write some stuff down. So we talk here about the idea of a one-sided derivative, and this is going to parallel really closely what we talked about with continuity on a closed interval as well. So if we say y equals f of x is differentiable on a closed interval a to b, if it is differentiable at every interior point, and then the way we deal with the endpoints is we're going to say if the derivative as we approach a from the right, which we would refer to as a right-hand derivative, and RHD is universally understood as an abbreviation for this right-hand derivative, and the limit as x approaches b from the left of f of b plus h minus f of b of h, which is known as the left-hand derivative, if those exist at the endpoints. So the question then comes up is, for example, is the derivative of a semicircle, does it exist at its endpoints? So here is an example of a semicircle, y equals the square root of 4 minus x squared, and our question then is it differentiable? Does the derivative exist here at the endpoints? So you can kind of see as you work your way from left to right, or from right to left, that, you know, the slopes of those tangent lines are becoming steeper and steeper negative. So the question is, right there at that endpoint, does it go straight vertical and be undefined since the slope of a vertical line doesn't exist? Or is it some really big finite number there? And so we can do this by using what we know about taking derivatives. We can still use our power rule and chain rule. So if we take the derivative by taking 1/2 times 4 minus x squared to the negative 1/2, and then using our chain rule times the derivative of negative x squared, then we can cancel the 1/2 and the negative 2. So that's going to be a negative x over, and then we get this square root of 4 minus x squared in the denominator. So then when we look at this, as we have seen up in here, so as we let x approach negative 2 from the right, you can see as you plug in numbers that get closer and closer to negative 2, the numerator is not going to 0, but the denominator is. And so when that happens, then we say that is going to go to, and it looks like that's going to be a negative negative, is going to go to infinity, a positive infinity. But whether it's positive or negative infinity, either way, that limit is not going to exist, which means that derivative on that left-hand derivative there, or I guess this would be, right-hand derivative here, this right-hand derivative does not exist. And so the derivative of that semicircle at that left endpoint doesn't exist. We could also say then that this function is not differentiable at x equals negative 2. And we're going to have the same issue that happens when we approach 2 from the left, because you're going to get that numerator is going to be negative, but this denominator is going to be going towards 0. And so you can kind of see the slopes of the tangent line here are going to fall off the cliff, and that left-hand derivative is going to go to negative infinity, which means it does not exist. And so the derivative does not exist there. Okay, so that's the whole idea of this left and right hand derivative. We can use this also to talk about other points, in particular looking at piecewise functions. So I'm going to give you a few piecewise functions here. I'm going to pause it and write 3 of these down, and then we're going to try to talk about that idea of, does the derivative exist where the pieces come together? So as we look at these 3 functions given here, the white, the yellow, and the blue, then our question is, does the derivative exist at x equals 0? So does the derivative exist at x equals 0? Now, it's important to remember that in order to be differentiable, it must first be continuous. So we want to check for continuity first, because if a function is not continuous, then it can't be differentiable. So on the first one, on the white one, if we plug in 0 into each of these, then 0 squared is 0, and 2 times 0 is 0. So these 2 pieces are equal to each other, and so that means it is continuous. So I'm going to ask continuous as a question, and then I'm going to ask, is it differentiable? Does the derivative exist? That's the second question. And so for the white function f of x, we can say yes, it is continuous. So once we pass that threshold, that test, we move to the next level, which is checking for differentiability. So we're going to take the derivative on the left, where we have x less than 0. So I'm going to say the left-hand derivative is going to be 2x, and if we evaluate that at 0, we're going to get 0. And the right-hand derivative is going to be just 2, and at x equals 0, 2 is still 2. So since the left-hand derivative is not equal to the right-hand derivative, then the answer to the question, does the derivative exist at 0, is no. So continuous, yes. Differentiable, no. Now the middle one, the g of x, so we first check for the continuity piece. And so again, to do that, we're going to plug 0 into the first one. So we get 0 squared is 0, and 0 into the second piece, and that's also 0. So yes, the function is continuous. So then we check for differentiability. And so we're going to take that left-hand derivative, which is going to be 2x, evaluate that at 0, and it is equal to 0. So we check the right-hand derivative, which is 3x squared, and evaluate that at 0. It is also 0. So the derivative does exist. So I'm going to say just, I'll say differentiability, and the answer to that is yes. So it is both continuous and differentiable. So what's kind of happening here, if you kind of imagine, I'm going to give you maybe a quick graph of first f of x. So f of x, we have it's x squared to the left of 0. So we know it's going to look like a parabola. And then it's going to become a straight line to the right, 2x. So they are in fact connected there. That's the continuity piece. So you can see they do come together and meet. But you can see that as you come in from the left, the derivative is going to approach 0, but on the right it's always 2. And so that creates then a corner point, because the derivative on the left is a finite number, but different than the finite number we get for the derivative on the right. So that's a corner point. Now, going on to the blue function, h of x, so here's where you want to check the continuity first. And so if you ask that question first, you can see that on the left, as we plug in 0, this is going to be 2. But when you plug in 0 on the right, you get 0. So these two are not going to meet. They're not going to connect. So it is discontinuous. Since it is not continuous, you don't have to do any more work. The answer to the differentiability question has to be no as well. Now, if you weren't being alert and looking at the continuity issue, you could look at the left-hand derivative and see that on the left, when you take the derivative of 2, you get 0. The right-hand derivative is going to be 2x, which at 0 is also 0. So you could be mistaken and say that it was differentiable if you neglected to consider the continuity piece. So what's happening here in terms of a graph is to the left of 0, this thing is always the horizontal line 2. And on the right, we're going to get this parabola that looks the half of a parabola. So their tangent lines, as you come in here, are both going to be 0, but because they don't connect, they are not differentiable. Okay, very good.